Hello mathematicians, welcome to this video lecture on Theorem 3, Taylor's Theorem with Remainder. What I'm going to do here in this lesson is walk you through Theorem 3, Taylor's Theorem with Remainder that we did in class on Thursday and Friday, as well as recap with an example the three different methods we have for finding error bounds for infinite series. Okay, so for those of you who were not here, this should be very useful to you, and if you just want a refresher on what exactly we're talking about with Taylor's theorem, I highly suggest you watch this video. So let's get right into it. So Theorem 3, we've previously seen two ways for finding error, and I'm going to recap that later, but we've seen one for geometric series, and we've seen one on the previous page for an alternating series. So if we have an alternating series that fits a few criteria. So if you have either one of those, a geometric series or an alternating series with certain criteria, you can use those ways of bounding the error. But if you don't have those, if you just have some general formula, a Taylor polynomial, you don't have a specifically geometric or alternating series, then you're going to need to know about Taylor's theorem with remainder. And here's what it says. Now I would copy this down into your notes packet if you haven't already. But if f has derivatives of all orders in an open interval I containing a, then for each positive integer n and for each x in I, we have the following. Okay, the first thing I'm going to write down is going to look just like Taylor's formula. Okay, previously, if you can take all derivatives of f, then we know that f of x is equal to an infinite series centered at a, and then we use Taylor's formula. It starts with f of a, then we start taking derivatives, f prime of a, times x minus a. Then we take another derivative, f double prime of a. And then as you take the next derivative, forgot the a there, then you need the powers to increase. It will be squared as well as factorial. And we'll just do one more for good measure. F triple prime of a times x minus a cubed over 3 factorial. So this is Taylor's formula, and it continues. And this equality holds, we can say equal to, if we're talking about the infinite series. If we're going to truncate it, then we would just say approximately equal to. Let me see if I can move this over a bit, just because we're going to need a little more room. Yeah, I'm going to do that for you. Okay, and see if you can squeeze this into your box. It continues. We can have, n terms by taking the nth derivative of a over n factorial x minus a to the n. And this is Taylor's formula. What I'm going to do here is normally I would put an ellipses after this and say ... again. If it's infinite, then it's equal. But we're going to say it's not infinite this time. Suppose you stop the series there. Okay, you have a polynomial up to this point. This is a Taylor polynomial. Okay, it stops at some n. It doesn't go on forever. Well, I can still say this is equal to if we have an adjustment term out here, or some error term, or some remainder term. That's where you get the idea of Taylor's theorem with remainder. And we just call that remainder term Rn of x. Some expression of x is that remainder term. Okay, the next part of this theorem. So this previously, you saw most of this before, but now we're stopping the polynomial and we're saying, yes, the polynomial is approximately equal to, but if we add some remainder, whatever that number happens to be, it'll be exactly equal to. And we can say something about this remainder. This is where this is important. Where Rn of x, we actually have a formula for it, must equal, and we're not going to prove this formula in this course, but you will in higher level analyses courses. You might prove something like this. But the remainder is equal to the nth plus 1 term, evaluated not at a, but at some c, times x minus a to the n, plus 1, or sorry, they're all n plus 1, they have to match here, over n plus 1 factorial. So the remainder term is equal to the next term evaluated at some c with the appropriate x minus a power as well as the appropriate factorial that matches that term. We can also say some more. for some, we could say something about this C. For some C between A and X. Okay, and that is the theorem. Some important things to know. This Rn of X term has some alternative names. So let me make some room here for that. Just going to move everything up. Okay, let me just type it because it's quicker. But that Rn of X term is called the truncation error. Write that down. It's also called the error term. It's also called the Lagrange form of the remainder. And I'm going to make this a little bigger so you can see it. But there we go. Lagrange form of the remainder. That's usually how you're going to see it put in your textbook. In Taylor's formula, the Lagrange form of the remainder has this. Now, underneath I have interpreting this theorem, where we're going to make a couple remarks about it. So I'm going to delete these hypotheses, and let's talk about interpreting this theorem. Let me just make a couple remarks of what it says, or what we could use it for. And the first is that, one, it gives us a formula that we can use for the error of any Taylor series. Okay, so we have a formula for error no matter what the Taylor series is. Take note of that. Second, the really important question hopefully you're asking yourself is, I kind of just said where f to the n plus, or f the n plus first derivative is evaluated at some c that's between a and x, but what is c? And that's what we're going to encounter when we do a couple examples next. Okay, what is this c? And it turns out there's actually an interesting answer to this. Let's see if I can give it a different color. Let's go with the pen. And it turns out that a lot of times we're not going to know what c is. Okay, I don't know. So the question is, well, then how do we know what the error is? Well, we don't know what c is, but because we know where c lives, it has to be between a and x. This allows us to bound c. Okay, so what is c? We don't know what c is, but we can bound it. We can find a maximum value for c, and therefore we can find a maximum value for the error. Okay, and what we're going to do in the next example is practice finding bounds for error based on a certain series. So you can skip the part below. We did not do the proofs. We're actually going to omit these because they're not essential for the AP test. But example 3 and 4, we're going to skip ahead in your packet. We're also going to skip the remainder bounding theorem as well as the proof underneath that for example 5. So we're skipping all the way ahead to example 6, and that's what we're going to do on the next page. Okay, so here's our next example, and I'll give you a minute. You can pause the video too if you need to copy this down into your packet. But it says, example 6, bounding the remainder in two ways. Suppose we use the first two terms of the Maclaurin series for f of x equals the ln natural log of 1 plus x to approximate f of 0.1. Find a bound for the error a using a, the alternating series bound, and b, the Lagrange form of the remainder. So we're going to do this in two different ways, and again, you can pause the video if you need some time to write it down. On the left side, I'm just going to make a little line down here. We're going to use the alternating series bound, and on the right side, we'll use that new Lagrange formula that we saw on the previous page. So let's see what this is all about. First of all, the first two terms of the Maclaurin series. This is a series that we're supposed to have memorized, ln of 1 plus x, but if you don't have it memorized, you can look back into your previous packet as well as your notes. But this is approximated with two terms, and they do alternate in sign, starting with x, and then it would be x squared over 2. There's no factorial on this one, and then it would be plus x cubed over 3, and so forth until you get to a dot, 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 and an nth term, whatever you like. But they ask us to approximate using two terms. Okay. Now, we don't actually care what the f of 0.1 is. That's not the purpose of this problem. The purpose of this problem is to figure out, well, what would be a bound for the error of this series? using the alternating series bound as well as the Lagrange formula for the remainder. So in other words, how good is two terms? Maybe we don't know exactly what two terms would give us, though we could plug it in and find out. But is there a rule or a formula, in this case alternating series and Lagrange, that we can use to find out how good this result is going to be? How good of an approximation is it? And so we use the alternating series bound. With that, remember there's three conditions. You have to check that it meets these three conditions. First, you need terms that alternate in sign, which we have. So that's a check. Second, you need terms that decrease in absolute value. And this is on your previous page of notes for the alternating series bound, but they decrease in absolute value. And that's a check, because if you plug in 0.1 here, 0.1 squared over 2, 0.1 cubed over 3, those things are getting tinier and tinier. As you raise 0.1 to higher powers, they get smaller. And the third thing is that the limit of the nth term also goes to 0. When you plug in the x, this is given as well. So the limit as n goes to infinity of, and then the formula here is x to the n plus 1 over n plus 1. But remember, we're evaluating where x is 0.1, so we're really checking out the limit as n goes to infinity of a tenth to the n plus 1 over n plus 1. You're checking that out, and you can quickly see that this limit is going to go to 0, because this 10 to the n plus 1 would jump down to the denominator, and the denominator is getting exceedingly large while the numerator remains a constant. So this limit does have to be 0, and then the alternating series will work. Okay, so these conditions are satisfied, therefore we can use the alternating series bound, which simply states, it is a direct formula, that the error is always less than the absolute value of the n plus first term, or the next term in your polynomial. And I should say here the next non-zero term in this case, because sometimes when you're thinking about sine and cosine, you know, they jump powers. They don't just go power of 1, 2, 3, 4. It's the next non-zero term. And in this case, we know that the error, I'll just say e, is less than, well, the next term would be x cubed over 3, which would be 0.1 to the third over 3. And we don't know exactly what the error is here, but we know that whatever the error is, sorry, it's a little messy there, it's going to be less than 0.1 to the third power over 3, which is equal to about, if you use your calculator, 0.0003. So we don't know what the error is, but we know it's that good. Okay, it's really good here. It's going to be exact out to 1, 2, 3 decimal places, and then there might be a little bit of error after that. But that's pretty good. So that's what this formula says. Now, what about the Lagrange form of the remainder? So consider this one now. It says you're going to take the nth plus 1 term of your Taylor formula, okay, and let's see what this ends up giving us. So just pause here for a moment. So when we're using this formula, and again, here I would say the alternating series bound is easier, but in some problems that's not available to you. So you are going to have to reckon with this Lagrange formula. Simply go component by component and see what you can plug in. So in this case, we know that this is going to be equal to the n plus first derivative evaluated at c. I'm sorry, we could do better than that. We know we already have two terms in our formula, since we're taking the first two terms rather. So this is going to be the third term that we're considering. And we have a power of 2, so we go to the next one, which will be x minus a to the third. And in this case, we know our x is just 0.1. And since it's specified that it's a Maclaurin series, we know our center is a, which is 0. So 0.1 minus 0 is our x minus a, which is just 0.1. And then that's to the third. And then over our n plus 1 is 3. So we're over 3 factorial. So again, we had two terms here. Therefore, we use 2 as our n. The next term to be n plus 1 would be 2 plus 1, which would be 3. So that's why we have a third derivative. We have to the third power, and we have 3 factorial. Now this third derivative, there's no easy way of getting around this. You are going to have to find the third derivative of the original function. Okay, so the original function is ln of 1 plus x. So you're going to have to do the derivative of that, which is 1 over 1 plus x. Then you have to do the derivative of that, which becomes negative 1 over 1 plus x squared. And then you do another derivative, and you will end up getting that the third derivative, and this will need to be calculated analytically, but it is 2 over 1 plus x to the third. That's what it comes out to be. All right, so in this formula, now remember what I said about c. We don't know what c is, but we can bound it based on the knowledge of this derivative as well as where c lives. Okay, remember c lives between x and a, if you look back at the previous formula. In this case, x is 0.1 and a is 0. So we know that c lives in here. Okay, 0 less than, I'll even say equal to, c less than or equal to 0.1. Actually, you know what, technically, since it says between, we'll take that to mean strictly between, but we'll talk about bounding in a second. You can use the endpoints. So we know c is in here, and so therefore, we're not going to be able to evaluate exactly f, the third derivative of f at c, but we can bound it. We can say that this expression has to be less than, and then we just need to find the maximum possibility for this term. What's the largest that can be? And then we'll multiply it by 0.1 to the third over 3 factorial. So what's the largest this term can be? That's what we need to consider next. And so if you look at this formula, it's a fraction. And as you make the denominator smaller, the fraction is going to get larger. So we want to see the smallest we can make this denominator, the smallest it's going to be. Well, we have to, these are the options. Okay, we're evaluating with c. We can plug a c in for the x. And we want to say what's the smallest this denominator can be so that we can maximize this whole fraction, maximize this term. And hopefully you'll see that if you let c equal 0, that's the smallest you can get. Now in reality, we know c is not actually equal to 0. But since we're doing the bounding, we just need something that we know for sure is going to be bigger than this actual term, okay, so that we can put this less than sign here. Okay, or you can even do less than or equal to be safe. Yeah, less than or equal to is what we'll use. And technically it could be equal to. But the point is we want to choose a value here that's smaller, makes the denominator smaller, which makes the whole fraction bigger, which means the largest this fraction can be, or what we'll use to bound it, is 2 over 1 plus 0, which simply gives us 2. Okay, and then we can simplify this term. The 2, there'll be a 2 that cancels out here with the factorial. So you'll end up getting, notice, 0.1 to the third over 3 is your error bound, and this is exactly the same thing that we got when we did the alternating series bound. Okay, so this takes practice of picking a c that works and using it, but it's an important technique for the Lagrange form of the remainder. Okay, we're going to pause here, and I'm going to do example 7 on the next slide. Okay, so here we're going to look at example 7, which is about bounding the error on an interval, another chance to apply the Lagrange formula for the remainder in a slightly different context. So let's take a look at the example. Copy this down into your packets. It says, suppose p sub 2 of x, I'm going to add some subscripts here, about x equals 2 is used to approximate f of x, and that the third derivative of f at x is always less than 2.3. The absolute value of that is always less than 2.3. That's a third derivative. For all x on the interval from 2 to 2.5. And now they're asking us to show that f of x minus p sub 2 of x is less than 0.5. All right, so let's break this down. And whenever you see the word show in math, they do want a mathematical argument. They want it to be tight. They want it to be accurate. You can call it a proof if you'd like, but that's what they're looking for. We want to show that that has to be true. You don't have to write the word proof, but we can here. First, just so you're aware, p sub 2 of x, that means the second order Taylor polynomial, or the Taylor polynomial that goes up to the second derivative, or the term with x squared, the term with 2 factorial, that's what we're talking about there with p sub 2 of x. And previously, from Taylor's formula, we know that f of x equals p sub 2 of x. But, I mean, that's not enough, right? If we just said that they're directly equal, it's approximated by p sub 2 of x. This would be false to say they're directly equal. So what we would say is, well, plus that remainder term, r sub n of x. Okay, and notice we're just talking in general here. We're not given the series as a natural log. We're not giving it a sine function. We don't know what it is, but some f of x, they gave us enough information to figure this out. Okay, and then we want to bound the expression f of x minus p2 of x, so you can do a little rearranging here and recognize that that's actually another way to isolate the remainder term. So f of x minus p2 of x is equal to the remainder term. Okay, we can take absolute value of both sides, preserve equality, and that's what we have. So we can bound this guy, f of x minus p2 of x, less than 0.5, if we can show that the remainder term is less than 0.5. So let's get to work on the remainder term. So we'll say this, which equals this, this equals this, and then we'll say which equals, going off of the remainder term here, just, Taylor's formula for the remainder term, f n plus 1 of c times x minus a to the n plus 1. And I know you can go right to substituting things here, but I think it's important when you're not fluent with the formulas yet, when you're not super comfortable, you practice writing them down. Over n plus 1 factorial. That's where we're at. That's a general formula. Okay, now we go to our substitution. Let's force ourselves. Let's consider what each part means. We know p2 goes up to the second derivative, p sub 2. So that means our n is 2 here, and the n plus 1th term will be the third derivative. So this says third derivative evaluated at some c. It's still an equal sign here because we're not going to bound that c term yet. And then given in the problem, it should give us our x and our a. So our x, notice we're going about x equals 2. But actually, yeah, some specific x is not given. So we know the center, right, because we're about x equals 2. That's the center of our Taylor series. But we're not actually given an x to work with. So that's an additional term we're going to have to bound in this problem. This is cubed, and then 2 plus 1 factorial, which is 3 factorial. Okay, so now's the important part to do the bounding. We've subbed in what we know, and we have to bound two different terms. By bound, I mean let's find an upper bound, something that they have to be smaller than, so we can write this less than sign here. Or if we want to be safe, we can write less than or equal to. We know at the most, whatever this term is, it's going to be less than or equal to something else. Okay. Perhaps you're seeing how to bound the the third derivative of f at c. Even though we don't know what c is, we know that c lives between x and a. So we don't know what x is, but we know it's on the interval 2 to 2.5. That's what we're talking about. And where a is 2. So the c has to be some number between 2 and 2.5. Okay, I apologize. I just remembered I forgot one statement here in the directions, which is important for me claiming that the c has to be between 2 and 2.5. So since we're talking about all x in that interval, so it should say show that f of x minus p sub 2 of x is less than 0.5 for all x in that interval. Okay, so we're only talking about the x's in here. Okay, so that's important. All right. So we don't know exactly what the c is, but we know c has to be between a, which is 2, and x, which has to be in here. Okay, so c has to be some number in here between 2 and 2.5. We don't know what it is, but we're given a way to bound it over in this portion of the problem. We're specifically told that the third derivative of x has to be less than 2.3. So I'm going to use the number 2.3 to bound the third derivative of f at c. But we also don't know this term. We don't know what x is, and since we want to bound, or maximize what's the maximum possible error that we can have, we want to maximize this term as well, x minus 2. So choosing from this interval, 2 to 2.5, how can we maximize this term? And if you try a few different values, you'll see that 2.5 is the way to go. If you plug in x equal to 2.5, you'll get 0.5 in that parentheses, and that's the largest that that term will be. And then we have over 3 factorial, which is 6. And then our hope is that this is equal to something which is less than 0.5. So let's plug it into our calculator, and you'll get it's about 0.048, which is indeed less than 0.05. Okay, and this completes the proof that the error term, or this absolute value of f of x minus p sub 2 of x, has to be less than 0.05. Okay, but again, what the main point of this is to get more exposure and practice to working with this Lagrange form or Lagrange formula for the error term and for bounding the error. And it'll take some practice to use that, but you'll need it on your homework problems as well as the alternating series test and those other tests. Okay, at the bottom of the next page of your packet, I'm just going to recap for you the 3 ways to analyze truncation error. So far we've seen you can have 3 different ways. You can have a geometric series. I would write this down into your notes. And for that one, we can find a formula. Let's put a dash. Find a formula for the truncation error. You can just stop the terms, let the terms continue, and the terms where you cut off or where you stopped looking at those terms, you can rewrite it using another power series. Okay, so if you look back at the early part of the packet, we used geometric series. So you have a series, or a polynomial rather, you cut it off, you have another infinite series, and you can factor it out using that a over 1 minus r formula to find a formula for the truncation error. So I'll actually just mention that up here. You will invoke a over 1 minus r in that process. The next way is the alternating series test, which we looked at in example 6. For that, you want to check, does it meet the 3 conditions? And then if it does, then you simply go to the absolute value of the n plus 1th term. Okay, and so then we can say that the error, if those 3 conditions are met, then the error is less than that, n plus 1st term. Last but not least, we have the Lagrange formula, which works with any polynomial, and it says that the error is equal to f of c times x minus a. Let me fill this in with the pen tool. We have f to the n plus 1 of c times x minus a to the n plus 1 over n plus 1 factorial. Okay, so the error is equal to that, which we're not really going to know what this c is, but we're given a way. The goal is to bound this term, and then we can find a maximum or an upper bound for the error. We don't know exactly what the error is, but we know it's no bigger than some other number. And those are the 3 ways to analyze truncation error with series. And I suggest you relook at the homework problems from B1, B2, as well as B3 for section 10.3 to become more familiar with the ideas and facts you need to know to complete these series problems. Feel free to email me for any questions you have, or to see me for extra help on Tuesday or Thursday this week. Thanks for watching this video lecture.